Okay, this is part 2 of section 5.3. In part 1, we studied phase planes for the system x prime equals ax when A was a 2 by 2 matrix in the case of complex eigendata. And in this part, we're going to focus on what happens when the eigenvalues of A and the eigenvectors are real. So our goal is analogous. We're trying to understand how the eigendata affects the shape of the solution curves. And in the case of real eigendata, it's much more explicit than it was in the case of complex eigendata. And we will focus in this discussion on diagonalizable matrices. And remember from linear algebra, when your eigendata is real, that means that you have a basis of, in this case, R2 made out of eigenvectors of A. In other words, you have V1 and V2 independent, where A of V1 is lambda 1 V1, and A of V2 is lambda 2 V2. Okay, so we know from previous material that in this case we get the corresponding solutions to the first order system, which are of the form e to the lambda 1 t v1 and e to the lambda 2 t v2. And the general solution to the first order system is made out of all linear combinations of these two basis function solutions. And when we're trying to evaluate the shape of the tangent field at V, it's helpful to express your vectors V and R2 using the basis V1, V2 instead of the standard basis. So if we write V as C1, V1 plus C2, V2, then the tangent field AV, which is what we get from the right-hand side of the first order system, is A times C1, V1 plus C2, V2, and AV1 is lambda 1, V1, so that's the first term, and AV2 is lambda 2, V2. So if the weights of a vector with respect to V1 and V2 were C1 and C2, the weights of AV are just C1 lambda 1 and C2 lambda 2. So that will help us understand what the tangent field looks like. The text also discusses the case when the matrix A is not diagonalizable. Remember from linear algebra that a matrix is diagonalizable if and only if all of the eigenspaces are non-defective, which means their dimension is the same as the power of the factor lambda minus lambda j in the characteristic polynomial. So when A is 2 by 2, the only way you get a non-diagonalizable A is if the characteristic polynomial is lambda minus lambda 1 squared, but the dimension of that eigenspace is 1, which is less than 2, which is what it would need to be in order for the matrix to be diagonalizable. We also today won't focus on what happens when one of the eigenvalues is 0. So we'll always be assuming that the eigenvalues are non-zero today. The text considers that case, and we might come back to it. Okay, so this first example is an example where the matrix A has two real eigenvalues of the opposite sign. And so let's start by finding the eigenvalues and the eigenvectors. This is, of course, review, but we first find the characteristic polynomial, which is the determinant of a minus lambda I. And as I'm looking at this determinant, the only lambda squared term comes from the diagonal product. It's lambda 1 lambda squared. In the diagonal product, I also see a minus 4 lambda plus a 3 lambda, which is minus a lambda. And then the constant terms come from both products in the determinant. So if the diagonal product gives me a minus 12, minus the off diagonal gives me plus 6. So that's lambda squared minus lambda minus 6, which factors into lambda minus 3 times lambda plus 2. So the eigenvalues are 3 and minus 2. And for the lambda equals 3 eigenspace, we want to solve a minus 3I equals times v equals 0, so that's a homogeneous problem. Substituting lambda equals 3 into the a minus lambda I get minus 6, 2, minus 3, 1. And I see that that a combination of the columns is 0. The two rows are multiples. If I take 1 times the first column plus 3 times the second column, I get 0. And since AV is just a linear combination of the columns where the weights are the entries of V, I deduce without having to go back to reduced row echelon form and back solving that the lambda equals 3 eigenspace is the span of 1, 3, the two weights in the equation at the left. And the eigenspace for lambda equals minus 2 is the null space for minus 1, 2, minus 3, 6. And a basis for that one-dimensional eigenspace is the vector 2, 1, because 2 times the first column plus 1 times the second column is 0. Okay, so now on the next page, we're going to use this eigendata information to sketch the tangent field. That we'll see is doable but cumbersome, and then we'll re-understand the phase portraits by just writing down the homogeneous solutions from the eigendata in part C and studying what happens to those parametric curves. Okay. So I just repeated parts B and C here. And remember the eigenspaces or the minus 2 eigenspace, which was spanned by 2, 1. And the lambda equals 3 eigenspace was spanned by 1, 3. And I was actually reading that off of the solution. So we know that each eigenpair gives us a solution e to the lambda tv. And so the e to the minus 2t times 2, 1 is a solution. And so is the e to the 3t times 1, 3. And because this is a homogeneous first order system, all linear combinations of solutions are solutions, and because the vectors 2, 1, 1, 3 are a basis for R2, these are all homogeneous solutions. Okay, so in part B, we're going to use the eigendata to start sketching the tangent field. So I'm going to sketch the two eigenspaces first. So I'll plot the point 2, 1, whose position vector is the vector 2, 1, because that's a basis vector for the -2 eigenspace. And then the eigenspace consists of all scalar multiples of that vector, which is a line through the origin. So this is the eigenspace for lambda equals -2. And similarly, the eigenspace for lambda equals 3 is the line through the origin containing 1, 3. Okay, so first, so for part B, we want to use the fact that, so the tangent field is AX, and we know that A, as from the previous page, times C1 times the eigenvector 2, 1 plus C2 times the eigenvector 1, 3 is C1 A of 2, 1, which is C1 times -2 times 2, 1 plus C2 times A of 1, 3. A of 1, 3 is 3 times 1, 3, so I get 3 C2 times 1, 3. And so if I'm looking along the lambda equals -2 eigenspace, that means that the C1 is not 0. Actually, here the C1s are positive along this curve. Here the C1s are negative, and the C2s are 0 when I'm writing V or X using the basis 2, 1 and 1, 3. And along the half of the eigenspace where C1 is negative, C2 is also 0. Let's do the same thing for the lambda equals 3 eigenspace. So along this upper curve, the C2s are positive because I have positive multiples of 1, 3, and the C1s are 0. And on the other half of that eigenspace, the C2s are negative and the C1s are 0. And the four sectors that I get between the four rays coming out of the origin are kind of like quadrants. And in this first quadrant, which we would, in analogy to how we name quadrants in the standard basis, in here, the C1s are positive because I'm going along the positive direction of the -2 eigenspace, and then I'm going in the positive direction of the 1, 3 vector as well. So, for example, if I added 2, 1 to 1, 3, I would be at this point, which is 3, 4. And anywhere in that quadrant, the C1 is positive and the C2 is positive. And as I go around the other 4 quadrants, the signs of the C's change analogously to how they do in the standard coordinate system. Okay, so since I drew in that point V1 plus V2, it's the point with position vector of V1 plus V2. When I evaluate the tangent field there, my two weights are 1 and 1, and so, well, actually, I got ahead of myself. Let's fill in the tangent field along the eigenspaces first. So, for example, at 2, 1, the weight of that with respect to my eigenbasis is 1, 0, because I have 1 times 2, 1, and 0 times 1, 3. And so A of 2, 1 is just minus 2 times 2, 1. And so that's a vector pointing back towards the origin from the point 2, 1, and I'll scale it so that that's its length. And then if I take A times half of that vector, I'll get a vector half as long. If I take A times twice that vector, I'll get a vector twice as long. And if I take A times the opposite of 2, 1, I'll get the opposite tangent vector. This is analogous to what we were doing with the complex eigendata. If I take A times the opposite of half of 2, 1, I'll get half of that, half of A of minus 2 minus 1, and similarly, the directions of the eigenvector, of the tangent field stay the same along these halves of the eigenspace, but the lengths just get scaled according to how far away I am from the origin. Okay, now let's do it along the lambda equals 3 eigenspace. So A of 1, 3 is 3 times 1, 3. So at the point 1, 3, I will have a longer tangent vector than I did at 2, 1. I say it's about that long if I'm using the same scaling as I was before. And then A of half that vector will be half of A of the vector. So at 1/2, 3/2, the vector's half as long. And A times minus 1 minus 3 is the opposite of A of 1, 3, so that vector is the opposite of the one I drew in the first quadrant. And similarly, when I scale the points, I just scale the tangent vectors the same way. Okay, so that was a lot of work. Now let's see what the tangent field looks like between the eigenspaces. And so let's go back to that parallelogram I drew. So the tangent field at V1 plus V2 is the sum of the tangent field at V1 plus the tangent field at V2. That's from this formula where the C1 and C2 are both 1. So I take the arrow that I had down at 2, 1, and then I add the displacement arrow that I had at 1, 3, And so the resulting sum is this vector. Okay, and if I had looked at what happened maybe at the point 2v1 plus v2, which is here, then I would be adding this longer green arrow to the green arrow from the -3 eigenspace. So let me do that. So it's something like this plus this plus this. And the resulting arrow from vector addition is that. And now let me, to emphasize what's the tangent field and what's not, let me turn these guys brown so that we only see the green resulting vector. Okay. And then if we take scales of those two vectors, I get the same scaling of the tangent field. So if I take half of v1 plus v2 and plot the tangent vector there, and so on. Okay, so we could continue this process, and what will happen is that our arrows tend to start bending as we approach the eigenspace. So we'll get a picture like that, and like that. And we could fill the whole thing in, but it's kind of tedious. I just wanted to show you that in principle, we could fill the whole tangent field in. I'm going to show you a quicker way to understand what the phase portraits are, and that's part C. So remember, x of t is c1 e to the lambda 1 t v1 plus c2 e to the lambda 2 t v2, which I should have written what they are in this case. c1 e to the minus 2t times 2, 1 plus c2 e to the 3t times 1, 3. Okay, so now we're looking at the second picture. Well, all C1s and C2s are possible. So for example, if C1 is positive and C2 is 0, then my curves are just living in the positive part of the -2 eigenspace. So I'll just redraw the two eigenspaces because they're also going to be related to the solution trajectories, as we'll see in a second. So that's the -2 eigenspace, and that's the lambda equals 3 eigenspace. Okay, so if C1 is positive and C2 is 0, then my solutions are just traveling from the positive part of the -2 eigenspace towards the origin because of the e to the -2t term, which sends the solution to 0. The second part's not there because C2 is 0. And if, so here C1, just as before, is positive and C2 is 0. On the other half of that eigenspace, the C1 is negative, and the C2 is 0. And, but again, the decaying exponential means that the solution converges to the origin. The opposite happens on the lambda equals 3 eigenspace. So the upper half of that is when C1 is 0 and C2 is positive, but then the e to the 3t is growing, so the solution, which is just C2 e to the 3t times 1, 3, goes to infinity along that eigenspace. And in the other half of that eigenspace, the C1 is 0 and the C2 is negative. And so the solutions, which are just a negative number times e to the 3t times 1, 3, head off to infinity in that direction. Okay, now what's always true is that as t goes to infinity, this first term is going to go to 0 no matter the value of C2. And so this is going to 0, so x of t it's converging to the lambda equals 3 eigenspace but it's also converging to infinity. So it's asymptotically converging to that eigenspace, is an asymptote for the parametric curve. And so, for example, if I started at the point 2, 1 plus 1, 3, so the C1 and the C2 are both 1, then as t goes to infinity, the solution trajectories are converging asymptotically to the lambda equals 3 eigenspace. And as t goes to minus infinity, then x of t is converging to the lambda equals minus 2 eigenspace and to infinity, because in that case, the e to the minus 3t term is going to 0. So if I take that same trajectory that I was drawing before, if I go backwards in time, the curve came from the minus 2 eigenspace and infinity. Okay, so in this quadrant, C1 and C2 were both positive. Okay, well, you can do the same analysis for the other 3 quadrants, and the limits as t goes to infinity will still have the same eigenspace quality. So, for example, in this quadrant, solutions come from the minus 2 eigenspace, and they go to the lambda equals 3 eigenspace. And I'll just fill in the other pieces, the arrows in the eigenspaces tell you what happens. Okay, now we know that solution curves with given initial points are unique and can't touch each other by the uniqueness theorem. So you can see that if I scale all of these curves, they will touch, so either by positive or negative scalars, they'll touch every point in R2. So every solution trajectory is just a rescaling of one of these. And I could draw some more in if I wanted to, or I can just use that abbreviated picture to illustrate what's happening. Okay, so here we just use the eigendata geometry, the eigenspaces, and the signs of the eigenvalues to draw a picture of what was happening. And let's see how it compares to p-plane output. It's almost exactly the same. Well, we didn't fill all of this in, but you can see if you look at the first quadrant that it looks like what I was at least trying to say. And by tracing the solution trajectories and the eigenspaces, we qualitatively really understood what all the solution trajectories look like. So proof of concept. Okay, so now what happens when the eigenvalues have the same sign? So let's look at this example, and we're all experts at finding eigendata, so just take it on faith or check it on your own, that the eigenspace values are 3 and 6, and they're given as the spans of the indicated vectors. So now let's write down the general solution that we get for the first order system of differential equations. Again, it'll be all linear combinations of e to the lambda tv for these two eigenpairs. So we get C1 e to the 3t times minus 1, 2 plus C2 e to the 6t times 1, 1. Okay, now we're not going to waste our time by trying to draw the tangent field. We'll just draw what the solution curves look like. And we begin by adding the eigenspaces to this picture. So one of them is spanned by 1, 1 or 4, 4. That is the lambda equals 6 eigenspace. And minus 1, 2 or minus 2, 4 is a basis for the other eigenspace. So I guess I can label 1, 1 and minus 1, 2. Okay, so the points that I get using those position vectors and all scalar multiples give me the eigenspace for lambda equals 6. Okay, so my solution trajectory, lambda equals 3. Okay, so if the C1 is not 0 and the C2 is 0, then my solutions are just multiples of e to the 3t times minus 1, 2. If those multiples are positive, then I'm on that half of the eigenspace, and my solutions are heading off to infinity. And if my multiples C1 are negative, then I'm on the other half, and my solutions are heading off to infinity. I'll erase that arrow. Okay. And the complementary case, when the C1s are 0 and the C2s are not 0, my solutions are running along the lambda equals 6 eigenspace, and they're also running off to infinity because of the e to the 6t, so I get arrows like so and like so. Now let's think about what happens as, let's first think about what happens as t goes to minus infinity. So in that case, the exponentials in each term are going to go to 0, so x of t goes to 0, but the e to the 6t term goes to 0 faster. Remember, t is going to minus infinity. So when t is really negative, both terms are small, but the e to the 3t minus 1, 2 term is much bigger. So I could say this by saying x of t over the magnitude of x of t is converging to a multiple of minus 1, 2. And geometrically, what that means is that the solution trajectory as t goes to minus infinity is going to the origin, but it's coming in along the lambda equals 3 eigenspace. So something like that. So I'm drawing different solutions in each quadrant. So, oops, this is S. T goes to minus infinity, so I'm going backwards compared to the arrows. Okay, now let's think about what happens as t goes to plus infinity. Well, then the e to the 6t term is growing much faster. Both terms are going to infinity, but the second one is getting bigger much faster. And so, in fact, if I took the unit tangent vector, x prime of t, over the magnitude of x prime of t, it would be converging to plus or minus, depending on the C2, the unit vector 1 over root 2 times 1, 1. The unit vector in the direction of the lambda equals 6 eigenspace. So in other words, as t goes forward in time, the curves are going to infinity. The contributions from each eigenspace are going to infinity, but the contributions from the lambda equals 6 eigenspace are getting much bigger than the ones from the lambda equals 3 eigenspace. And the tangent vectors are starting to look like the tangent vector to the lambda equals 6 eigenspace. So this is the picture that encapsulates that. And again, because these are homogeneous solutions, constant multiples of every solution is a solution. And if you scale these functions, you can go through any point you want in the plane. And so every solution curve is a rescaling of one of these. And we did pretty well. So here's a very small p-plane picture. Here was the eigenspace for lambda equals 6. And here was the eigenspace for lambda equals 3. And I just had p-plane draw a few more solution trajectories. But so we understand qualitatively, just in terms of the eigendata, pretty much exactly what happened. Okay, now, so far we've done the case of one positive and one negative eigenvalue, two positive eigenvalues. Now we're going to do two negative eigenvalues, and we'll save time by using this theorem about time reversal. So if you have the system x prime equals ax, then if you change your coefficient matrix to minus a, then if you take your solutions to the first system and take x of minus t and call that y of t, then y of t will solve that new first order system which has the opposite matrix. So in other words, if you take the opposite matrix, you get the same solution trajectories, they're just going in the opposite direction. Okay, and the proof of this fact is just the chain rule. So if we take y of t to be x of minus t, where x solved x prime equals ax, let's compute y prime. So we have to use the chain rule. Y is a composition. It is x of minus t. So by the chain rule, y prime is the derivative of the outside function, which is x prime, evaluated at the inside function, then times the which is minus t, times the t derivative of the inside function, which is minus 1. Okay, but x prime at any value, well, okay, so this can be rewritten as minus x prime of minus t. X prime at any value is a times x at that value. That's what the first differential equation said. So x prime at minus t is just a times x at that same t value. But then we also had the minus in front. Okay, so that gives this equality. And then x of minus t is what we were calling y of t. And so we can rewrite that as minus a times y. So y prime is minus a times y, just as we claimed. Okay, so let's see how that relates to our discussion. In example 3, we'll first do part A, which is more general than just this discussion, and it's something you might have discussed in linear algebra. And it has to do with how the eigendata of two matrices relate when one of them is a scalar multiple of the other matrix. So let A be a square matrix. Let C be a scalar. Then what's the eigendata for C times A compared to the eigendata for A? Well, suppose V is an eigenvector for A. So AV equals lambda V. Then let's compute the matrix CA times V. Well, by matrix properties, that's just C times AV, which is C times lambda V. And so what we see is that CA times V is not lambda V, it's C lambda times V. So if you multiply A, the matrix A, by the scalar C, then the eigenvectors stay the same. V was an eigenvector before, and it is now. But the eigenvalue changes from lambda to C lambda. So the eigenvalues are multiplied by C. So in part B, we're going to do the special case where C is -1. So let's consider this system in part B, and the matrix in that system is the opposite of the matrix in the system we just analyzed. So this is -A, where A was the matrix from the previous exercise. So we multiplied the matrix by -1, so the eigenvectors stay the same, but the eigenvalues become the opposite. So instead of an eigenvalue of 3, we have an eigenvalue of -3, but the eigenvector is what it was before, -1, 2. And the old eigenvalue was 6, so now it's -6. And we have the same eigenvector we had before, which was 1, 1. And remember, in the chain rule theorem, we saw that we get the solutions just by just replacing t with -t, or with, when we do replace a with -a. And we see that when we just write down the solutions here, which will be linear combinations, C1 times e to the -3t times -1, 2. Notice we replaced t with -t in the old formula, plus C2 e to the -6t times 1, 1. And when we draw what these curves look like, they're just like they were in the first example, but instead of converging to infinity, everything is converging to the origin. And we're traversing all of the old curves, but going in the opposite direction. So the picture of the curves without the arrows looks exactly the same as it did in the previous example. Okay, so that's all the cases where A is diagonalizable with real eigenvalues and the eigenvalues are non-zero. The first case we considered was when they had the opposite sign, and so if lambda 1 is the -1, so the solutions are those linear combinations, and if lambda 2 is the +1, then the solutions are converging to the lambda 2 eigenspace. So seeing what the arrows are doing, I can see that this is the eigenspace for lambda equals 2. And when t goes to -infinity, the e to the lambda 1 t terms are going to infinity, and so where I came from was tangent to the lambda equals lambda 1 eigenspace. Okay, and in this case, we say that the origin is a saddle point, and this is a picture of saddle point trajectories. If you've ever looked at a topo map, you know that when you come to a saddle, that's exactly what the topo lines look like, where you came up a canyon to a low point on a ridge, and the ridge goes up in both of the other directions. And I guess in the old days, it was because of horse saddles. Okay, so the cases for lambda 1 and lambda 2 both negative or both positive, the blue curves look the same, they're just going in the opposite directions. When they're both negative, then every term in the solution x of t is exponentially decaying, and everything converges to the origin. So 0 is a nodal, what we call a nodal sink. Nodes are places where all the paths converge to that spot in this sort of a way. And we could figure out, I mean, I can draw the eigenspaces. You can see the eigenspaces. So that's one of the weight when one of the weights is 0. And by looking at how the curves bend in towards one of the eigenspaces, you could figure out which is the lambda 1 eigenspace and the lambda 2 eigenspace. Well, you'd have to know how lambda 1 and lambda 2 compare. I'll let you think about that, but you could do it. And analogously, if the eigenvalues are all positive, the x of t's go to infinity, and you get the picture that's just reversed of the one to the left of it. And you could figure out what the eigenspaces were. Okay, that is the end of this section.